Okay, so am I visible? Are the slides changing?
Yes, sir.
Anyone?
Slides are visible.
Are visible. They are changing?
Yes, yes. Alternate visualization is what I see.
Very, very good. Thank you. So let us continue with our discussion with Gaussian process. As we mentioned that a Gaussian process is an extension of multivariate Gaussian, where the number of variables, the number of variates can potentially go to infinity. So, I mean, I already went through this visualization in the last class. Let me come to the definition, recap the definition once more. Okay, so it is a multivariate Gaussian distribution over potentially infinite number of variables, and each of these variables, potentially infinite, can be thought of to be indexed. That means they denote some ordered quantities. For example, these variables may be time, they may be x. In general, we call them as independent variable x, and there is a ordering between them. There is a notion of distance between two independent variables. In general, when we consider a multivariate variate, we don't talk about distance between two, how close are two variables. But here we actually talk about index of variables. So potentially it is an multivariate Gaussian distribution over a set of variables where the number of variables may go to infinity, and we call it a Gaussian process if we take any subset of these variables, it will be a Gaussian distribution, by multivariate Gaussian distribution. All right, so if this property is satisfied, then this kind of infinite dimensional Gaussian would be called a Gaussian process. In other words, if we take this infinite, what is the meaning of if we take any subset of variables? That means if you marginalize it over any marginalization would produce a Gaussian, which is again a property of the Gaussian, normal multivariate Gaussian also. Another way of thinking of this is that each of these variables, say f1 to I call 1 to n, we can think of as points lying on some function like this. Each of these variables can be thought of points lying on these functions, and since each of these the joint distribution of these points would be a multivariate Gaussian, if we increase the number of points to infinity, we can think of the entire Gaussian distribution as a distribution over a function space. You can think of, if you take infinite points, it is infinite, and so each instance drawn out of this infinite dimensional Gaussian is one such function. So you get a collection of functions as instances, and the distribution, the probability of each of these functions being available in the sample is the distribution, is a Gaussian. So it can also be thought of as a distribution over the function space. But the formal definition is it is a distribution over any collection of points, indexed points, any collection of variables, rather index variables, such that any subset of the variables are also Gaussian. So we will usually go by the function space point of view. We'll also see that this is actually advantageous in the sense that it helps us visualize the things better, but we'll also sometimes subscribe to this subset joint distribution view also. A Gaussian process, just like a normal distribution is characterized by this mean and the variance, a Gaussian process is characterized by two parameters. One is called the mean function. Note that since it is a distribution in the function space, it is the mean and the variance are no longer constant, but they are variables, they are functions of the indices, the variables or the x, which we call the independent variables. So it has two parameters. One is called a mean, which is mean function, which is denoted by mx, and the other is called a Kernel function or a covariance function. We'll soon explain why it is we are calling it a Kernel function, denoted by some k x comma x prime. Right. So these are the two parameters. So let me explain what these parameters are. You come back to this. Let's say this example. All right, so it is an example where I have 20 variables, and you remember our earlier notation. What we did was the value of each of the variable I plotted along y-axis, and the index of the variable I plotted along x-axis. So this is one particular instantiation of the variables x1 to x20. I just draw them by some line for making it look like a function. Right. So so this is an instance drawn out of a Gaussian process, and these are the variables. So the mx would be nothing but, see, I said that every subset is a Gaussian. So every individual point is a subset. It will also be a Gaussian. So the mx function is nothing but the expected value of the x variable, of the variable at point x. So say x equal to 3. So this would be the m3 would be the expected value of the random variable at 3. All right. So now let us look at the, so that mx basically gives a kind of an average value. So if we take the function space point of view, it is kind of the average value at certain, or the expected value at certain point. Now let us look at the Kernel function, what it means. We said that this is a joint distribution between all these indices. So if it is a joint distribution means it is a multivariate, in this case 20-variate Gaussian. So we will have a 20 by 20 covariance matrix for a 20-variate Gaussian. And what are the covariance matrix entries means? The diagonal would mean simply the variance of each of these points. Say x equal to 1, 2, 3. For each of these points, the variance are the 20 variances. What about the covariances? The covariance between the ith variable and the jth variable, that is the ijth entry of this matrix, is basically how much is the covariance between this point and this point. So let us look at this distribution, this visualization. So take only 5 variables, right? So as you draw more and more samples of these 5 variables, more and more random 5-dimensional vectors, the diagonal term of this matrix would denote how does this individual point, how much does it wiggle, how much does it disperse, the dispersion of this single individual point. And the covariance, so ijth entry of the covariance matrix means you pick the ith point, pick the jth point, something like this, pick the ith point, pick the jth point. In this case, say I equal to 1, j equal to 2. How does if one changes by this much, how does the covary? If this changes, how much does this change? If changes a lot, does it mean, that means whether this joining line more or less does not change its orientation. If one changes, the other also changes by that much. They wiggle by the same amount. That means if it is high, that means they are highly correlated. The covariance value is very high. If the covariance value is low, that means they are kind of independent. That means if one of the variable, one of the index changes, the other need not follow that change. It can change in some other manner. Okay, So it means, so similarly, I can think of that here also. I can then think of that here also. That means, say this is one of the variable I and this is another variable j. So if we move I, how much does j change? The change is, if the change together, the covariance is high. If the change less, the covariance is less. All right. So this is like you can have an alternate visualization also. Let me try to give you the visualization. Yes. So let us think of it this way. So this is kind of a rope, a tight rope kind of thing. So this is a rope, and you are as if moving one point. You are moving one point. So the position of this rope would be at x would be mx. This I call as x, and this I call as y. The movement, I'll move the rope, so the movement I call as y. So this position of the rope would be mx, and sigma ij is that if you move this point in the, or rather sigma xi xj, let's say, if we move the point xi by certain amount, how much does, imagine a rope, you are seeking a point in the rope, and another point will also sec. If these 2 points have a high covariance, that means if this point secs by some amount, say 1 meter, this point will also sec by around 1 meter. Okay, that means sec this point equivalently secs in a rope. All right. So there are some natural properties of the rope that we can assume while writing down this covariance matrix. One thing we can see that if xi and xj are close, that means if this secs, this will also sec similarly. That means if this xi and xj are close, they should have a high covariance. Whereas if xi and xj are far apart, that means if this point secs, this may not sec so much. This may not sec so much. They are far apart. So that means if xi and xj are far apart, their corresponding covariance matrix, the covariance value might be low. Whereas if they are close together, say xi is 1, xj is 2, then it should be high. This is a natural property. You are free to choose any other form, but this is kind of a natural rope. Whereas if xi is 1 and xj is say 20 or 19, then it is not in this case, that is not the case, but we can make that to be small. So kind of we have a local effect. So a change in x will have a high covariance of a similar change in neighbors of x. And there, the far away from x, they will be kind of independent. If x changes, they need not change. Okay, so that's how our definition of this covariance. That's what we said. That this is a natural way of writing down this. You can always free to choose any other form. That still makes it a GP, but this is a natural form of the covariance matrix that one would be kind of expect in many situations. All right. So this is how you set your. So 2 points to be noted. So mx is kind of the expected value at x, and sigma xi xj is if xi changes by something, how much does xj change? How much does xj change? Okay. All right. So this is what, you see that these two are pretty non-correlated kind of thing. If this changes, oh no, this is correlated. Okay, anyway, I mean, I've not drawn them according to that locality preserving property, but that is a natural choice. So I think the meaning of this mx, I have not yet talked about k, I have just talked about sigma, still elements of a covariance matrix. So this is the intuitive meaning. So I repeat the intuitive meaning, mx expectation value at some point x, one of the parameter of the Gaussian process, sigma xi xj. I initially assume that is equivalent to k xi xj. I'll explain why it is so. Sigma xi xj is kind of the how much does the change in one point affect the changes in other points along the function. One natural choice of this, one natural property that xi xj that one might choose is that it is kind of, if xi changes, other xj's in the locality of xi also changes, have a high covariance, and far away don't have a high covariance, they are independent. All right. So now this is for 5 points on the function, 5 points on the function, and I have a 5 by 5 covariance matrix. As I have said, I can potentially have infinite number of points. So I can increase this number of points to infinity. So naturally, this covariance matrix will be an infinity by infinity matrix. So I could not do for infinity, but I have done for 20. And instead of writing down values, I have color coded them. Red is a high value, blue is a low value. But I would like to this number of points go to infinity. So this would become a big matrix. The thing is that if this matrix goes to, if the number of variables go to infinity, then I need not, actually it is difficult to write it down as a matrix or a table. It's just the covariance table you can think of. It is difficult to enumerate it as a table. But I can always write it down as a function. So I can always write this sigma between ith variable and jth variable. I can always write it as some function k between xi, xj. Okay, so if I know this function k, and then I need not waste memory for storing this table, storing this matrix. Because what then I'll do is that I can reconstruct this covariance matrix for whatever xi, xj I want. I'll just pick up xi, I'll pick up xj, plug in their values in this function, and get the corresponding entry. Right. So this kernel function is nothing but a functional form or a non-enumerated form or a functional algebraic form or a functional form of the covariance matrix. And as before, as I said, this covariance matrix captures the how if one xi changes, how much does xj change. This kernel function will actually now can capture that effect. So if the kernel function is so defined that if xi minus xj is large, its value is small, then we don't have a far effect. And if k is high, if xi is close to xj, xi minus xj is small, then the covariance is high. I can now just assume different forms of k to take care of different types of sigma function. Okay, so this is the meaning. So as I have said, is that my so this is the interpretation of this mx parameter of the GP and the kernel function we call kx comma x prime function of the G. So this is the mean, and this is the kernel function, which is kind of same as the covariance matrix. Kind of same, not thing. Okay, So now we'll soon see a functional form of this covariance matrix. Okay, let us see a functional form of this covariance matrix. Well, this is another way of saying, this is saying, so if x1 to xn are a set of points on the function, and if we pick up the values of the function fx1 to fxn, what Gaussian, if f follows, if f is drawn from a Gaussian process with mean mu and kernel function k, it means that this vector, what is this vector? This is the y-axis value in the previous diagrams I drew at x1, x2, up to xn. This is a n-dimensional vector. So that vector is normally distributed with mean mu1, mu x1, mu x2. Mean is a function. Mean is not a constant. Mean is a function which I evaluate at x1, x2, xn, and a covariance matrix which I calculate by. See, now I have x1 to xn, which I calculate by the plugging in the kernel function. x1 is the diagonal, x1, x2, x1, xn, and so on. I use my kernel function to compute this sigma matrix. Okay, so you take any set of samples. So this x1 to xn are any set of samples on f of the functions that you have drawn. You pick up any set of points, n points, and they will be jointly, their vector will be jointly distributed as this Gaussian by definition. Okay, let us look at some kernel functions. This is a I'll then come back to the use of this Gaussian process. This is a very common kernel function called a squared exponential function. A squared exponential function. So it takes this following form. K of, instead of xm, so this you can think of as xi xj, and this also you can think of as xi and xj. So k of xi xj is e to the power xi minus xj whole square, or let's go with ti tj. K of ti tj is e to the power ti minus tj whole square, normalized in the denominator by something called a 2L square. So this L square is a hyperparameter of the AC squared exponential. This is a hyperparameter, sometimes called the length scale parameter. I'll explain why it's called the length scale parameter. And this sigma f, the whole thing multiplied by some sigma f square, which is also an hyperparameter. Sorry, not length scale, length hyperparameter. This is sometimes called a scale hyperparameter. So you can actually always plot this value of ki k. So if I plot ti minus tj along the x-axis and k of ti tj would look, it always has to be positive, so it will be very high if ti close to tj and fall off thereof. Okay, and it is symmetric because we are taking the square. Even if it is negative, it will fall off in the similar way. Let us look at some possible values of sigma f and L. Let's say sigma f equal to 7 and L equal to 100. And you choose to be, say, 700, 31, 32, 33 to be 700, 800, 1029. And if we plot, so I'll get a, since there are three variables, T1, T2, Tj, I should get 3×3 covariance matrix. And this is my covariance matrix. If I plug in these values to this equation, you see I get some diagonal elements, all same, and some off diagonal elements. Off diagonal elements, you see, 1 and 2 are having a very high value, whereas 1 and 3 is having a relatively low value. Okay. Now let us change the scale parameter. I have kept sigma f to be still to be 7. Here also it was 7. L was 100. Now I made L to be 500. That means, and the effect you see that the closer values, 1 and 2, it was high. The further values, 1 and 3, was less. Now the 1 and 2 value has increased by some amount, say double, whereas the 1 and 3 value, the thing which is between 1 and 3, the covariance, that has increased a lot. If we make L parameter from 0 to 50. So that actually means that if we take xi, xj, the L parameter controls how fast does this decay off. That means if xi is highly related to something very close and it is less related to something very far, if the value of L is very small, if the L is small, then this value decay, the distance to which a point has an effect is small. It decays very fast.
Excuse me, sir?
No, it's the other way around, I think. It's the other way. Tell.
Sir, these hyperparameter values for sigma and L, the length and hyperparameter, and we take 7 and 500 are extremely randomly, or there is some.
No, I am explaining as an example.
Okay. Okay.
I'm trying to study the effect of sigma and L in this covariance matrix.
Okay.
So the thing actually, I mean, I need not have taken so many examples. If you just look at the function only, it's obvious. So the higher the value of L, the faster it decays. The higher the value of, am I making a mistake? No, I think the other way around. The higher the value of L, the further you have your effect. Okay, so this change here. So the covariance between, I plot the covariance, let's say, between this point and the other points. It will decay, it will stay till long. Whereas if L is small, it will decay faster. All right, so that means if I chose to be L, the rope that we talked about is very local. The changes are, say, they die out beyond a locality, small locality. Whereas if L is large, they do not die out over a small locality. They stay, they affect further points also. Okay, and now let us look at this sigma f. So sigma f, as you can, I have changed sigma f from 7 to 14 in this case. You see it changes the diagonal elements of this matrix, covariance matrix. So what is the diagonal element? Diagonal element is as if what is the variance of x itself, not the covariance, not with other points, just that point on the rope, what is the variance? So this sigma f is kind of a scale parameter. It determines the width of the variation at every point in the function. So if it is high, the width is high. How much does the band of the function is high? How much does it can vary at a single point? So L sometimes is called a smoothness parameter, because if L is high, that means a change here will make a lot of, the function will be kind of flat. Everything will be the same. If L is low, then the changes are only local. The function will not be very smooth. There will be local vacillations or oscillations. Whereas the sigma control, if the sigma is less, the rope will only vibrate in a small band. If the sigma is high, it will vibrate a lot. The amplitude will be high. So here are some examples. So this is, you see, sigma equal to 10. It has a high variation. Whereas sigma equal to 4 has a smaller band variation. So these colored lines are all the instances of the functions drawn from the corresponding GP with hyperparameters this and this. And this is kind of a 2 sigma bound on the functions where they will lie, inside which band. So this is kind of, all functions should lie in this band with a high probability, this shaded band with a high probability, all the sample functions. So you can see that if L is 50, the variation is same. If we and if sigma is 10, it is this much. If sigma is 4, it has reduced. If I reduce the value of L, I said the local influences are more. That means it becomes less smooth. There are more local variations. It is more jittery. It is whereas if you have increased L even further, this function would have been even smoother. Right. So these are the kind of experiments, and these are kind of course, GP is a distribution. What I have drawn here are samples drawn from this distribution. Okay. So anyway, so this is well, the squared exponential is just one form of the kernel. The point to be noted is that I have parameterized the kernel matrix, the enumerated kernel matrix, to a function. I can always reconstruct the enumerated kernel function matrix by plugging in values to this function. But the advantage of this function is that it is kind of a succinct representation of an infinite dimensional covariance matrix, and kind of implicit representation of an infinite dimensional covariance matrix. That's the point. That's the important observation.
Excuse me, sir.
Yeah.
Sir, in the kernel, this thing, what is the vector t? Is it the marginal variance of each of the indices?
No, these are the value of the indices.
But each of the t, I mean,
Okay,
each of the
let
ti
me explain.
itself.
Let me explain. So say this is t equal to 100, t1, let's say called equal to 100. This is say t1 equal to 200, t2 equal to 200. Okay, so this is t3 equal to 300. These are the 300. So t1, t2, t3, this vector is 100, 200, 300. These are, and because this entire thing is a Gaussian process, the distribution of this would also be normal with some mean and sigma. How do you get this mean? This mean is also a three-dimensional vector, mu1, mu2, mu3, which is the expected value of this function at this point of this. Yeah. Expected value of the function at this point is mu1, this point mu2, this point mu3. And what is sigma? Sigma is the diagonal entries at the variance of this point, variance of this point, variance of this point. What are the off-diagonal entries? Covariance between this point and this point, this point and this point, this point and this point. That's the thing. That's the I just draw 3 points from this Gaussian process on this function. And I know by property of Gaussian process that these 3 points would be a trivariate normal. That's it. Okay, I think that was not your question. What is your question?
Yeah, so sir, I just got confused. I mean, say for if we want to plot the covariance matrix for 3 features, first, second, and third, so then we'll take t1, t2, t3 as 1, 2, and 3, right?
Yes. So the covariance matrix here would be, it be k of t1 comma t1, k of t2 comma t2, k of the entire covariance matrix I can use compute using the covariance kernel function t3 comma t3, and this would be k of, I just plug in the values of t1 and t2. This would be k of t1 t2. This would be k of t2 t3, like this.
Okay, sir.
I just see that's the advantage. So you can think of this as an projection of the infinite dimensional space to a three-dimensional space.
Okay, but sir, this kernel function will then inherently assign very high covariance between closed indices, right?
If we design your exponential function that way,
Okay.
if you design your this squared exponential function that way, if L is, for example, if L is very high,
Right.
then the local effects will not there. Whereas if L is very low, only a small locality will be affected.
Okay.
It will not affect a further point.
Okay, sir. Okay. Clear, sir. Yeah.
That means if you take 2 points far away, they are kind of independent of each other. They do not depend on each other.
Right. Okay, sir.
What is the meaning of almost zero variance? Huh? Okay.
Yes, sir.
All right. So this is just one form of the kernel function. You can also choose other forms. All right. So now the next question possibly will be that can I choose any k to be a valid kernel function? The answer is actually you cannot choose any k as your kernel function. One property that should be satisfied is that whatever may be your kernel function, and you can use the kernel function to compute any covariance matrix, say 3 by 3, 5 by 5, 2 by 2, at any T1, T2, T3. You can choose your T1, T2, T3, or maybe T1, T2, T20. You can choose any kernel function. You can choose any covariance. You can instantiate or calculate any covariance matrix using this kernel function. If it is because one of the property that this any covariance matrix should satisfy is that there has to be something called positive semi-definite. Positive semi-definite. That means if I call this, if you pick up any vector x, and if you take this covariance matrix sigma and you multiply by x transpose, this has to be greater than 0. This actually is a requirement that if you remember the expression for the Gaussian probability distribution, it is something like proportional to something like e to the power x minus mu by sigma square. Instead of by sigma square, I am writing sigma inverse. Sorry, this is wrong. It is something like x minus mu sigma inverse x minus mu transpose e to the power to the whole negative of all this thing. So if sigma is positive, then only this exponential term is positive and the negative of that is negative. That means it is a decaying function. If sigma was not positive definite, this could have been a diverging, increasing function, which we don't want. Then it is not a valid Gaussian, right? So for a Gaussian, this covariance matrix always has to be positive semi-definite. So whatever function you choose, you have to ensure that any sigma you construct out of using that kernel function has to satisfy this positive semi-definite property, because any sigma function has to satisfy this. Actually, there is a lot of complicated mathematics to show that this will be the case when your kernel function is something called a Mercer kernel. Mercer kernel. The condition is little bit tricky. The condition is something like this. If you compute this definite integral k of xi, xj, and take any square integrable function of xi, xj, and do a double integration over xi, xj, and similarly you have a double integration here. This entire thing should be bounded. If you can show that, and this should be so true for all fx in something called a square integrable function, which I call a Lebesgue integrable L2 functions. Square integral functions means this integral fx dx is bounded. Okay, so for any such f, this double integral should be bounded. So if that is so, you call a valid Marshall kernel. Most of the normal functions that we'll use will follow this property, though it's quite difficult to establish this property. But why we need this property is that because any sigma that we construct using this function has to be positive semi-definite. Otherwise, it's not a valid Gaussian distribution. Okay, so this is about the nature of the Gaussian process. I think I have spent too much time on it. All right. Why we are choosing this Gaussian process? Again, I mean, most of the processes in nature are Gaussian processes, but there are some advantageous properties also of GP. So if we take one Gaussian process, say, actually, this is a property of both Gaussian distribution and Gaussian processes. You take two Gaussian distributions, add them. So if you have one distribution in, say, mu1 sigma 1, and you have another distribution in mu2 sigma 2, say x1 is distributed along to, about this, x2 is distributed around this. So x1 plus x2, this random variable would be also as a normal with Gaussian mu1, mu2, mu1 plus mu2, and variance sigma 1 plus sigma 2 if x1 and x2 are independent. So if you add two random variables, their means just get added, their Gaussian variances just get added if these two variables are independent. All these arises from the exponential form of the Gaussian distribution. In fact, this is true for any exponential family. So product of two Gaussian is also a Gaussian. You multiply a Gaussian by a constant, it stays a Gaussian. If the joint distribution of two variables a and b are Gaussian, so are their marginal distributions p and pb, and so are their conditional distributions p of a given b, p of b given a. All these are Gaussians. All these can be easily worked out from the algebraic form of Gaussian. So, so these are very advantageous properties which we'll exploit. All right. So now, what does this mean? This actually means the important thing. Suppose I have a Gaussian process, something like this, and say A is, say, x1. This is A, and B is, say, another point x2. These two are some points on this, on the index x. Since if this is a GP, if this is a GP, then we know that any subset of the GP, that means if you pick up any 2 points x1, x2, that is a Gaussian distribution. So if we take x1 comma x2, this will be a Gaussian distribution by property of GP. All right. So, and if this is a Gaussian, then x1 is also a Gaussian by this property and also by property of GP. x2 is also Gaussian by property of GP, and x1 given x2 is also a Gaussian. You remember earlier we used to draw a picture that you slice. What is x1 given x2? That means suppose the value of x2 is given. So jointly they are Gaussian, and I fix the value of x2 to a constant. So I cut that thing. I fix the value of x2, assume it is given, it is no longer random. Then x1 is a Gaussian with some parameters, which you can calculate using x2. All right, so this is the picture. Let me quickly show you the picture. Yeah, this is the picture. Suppose I fix one of the variables, say y1, and look at the other, fix y1 to say 1. y1 to say 1 I fix. And the other variable, the other end of this curve varies as a Gaussian. with some mean and variance, which you can easily calculate from the value of x1. Right. All right. So this I can actually extend to this. I can extend. Let me. Yes, I can extend to this multidimensional case also. I can fix any two values and the other things can change. So the moment I fix any two value, it is like a conditional. That means what is the value of this given the value of x1 is 1, value of x2 is 1.5. Given the value of x1, x2, what is the value of this? Okay, so let us write it down. So this let me call as x1, this let me call as x2, and this point let me call as x3. Okay, so by these properties we studied so far, this x3 given x1, x2, given known values of x1, x2, that is a Gaussian by GP property. GP property plus by GP property x1, x2, x3 is a Gaussian, and by this conditional property that we talked about, if x1, x2 is given, then x3 given x1, x2 is a Gaussian. Any doubt? Have I skipped anything, or you are able to understand this? This is by this property that we are mentioning. Yes, this is by this property. Okay, so this is a very important discussion. Let me complete this. Right, so this is clear. This is clear. This will, if this is a Gaussian process, I mean, I think this is one advantage we exploit as by assuming it to be a Gaussian process. Right. So these red points values are given. This black point, I want to condition on them. I want to see x3 is still a random variable. Are fixed to be constant. x3 is still a random variable, but we know a lot about this random variable. We know that this random variable given value of x1, x1, x2 is a normal. That is a lot of knowledge about this normal variable. Not only that, you can easily calculate their mean and sigma. That is a lot of knowledge. That is all we need to know about this random variable x3 given x1, x2, this conditional. Right. So, what I want to say is that this can be easily computed using, if everything is a Gaussian process. This conditional can be easily computed. Okay. Next question. Why am I interested about this conditional? Suppose this is a time series of say temperature or some stock value. Okay, you know stock values are random variables. They can change. They have some variation and they have some cross variation. It depends on yesterday's variable. It depends on day before yesterday's value. There is some, the sigma terms are there. Sigma cross variance terms are there, and there is a everyday variation. Dispersion is there. Suppose these two are my training point. That means they are known observations of say stock on the 1st and 2nd of a month. They are say training observations. And x3 is a test observation that you want to predict for the 5th day of the month. 5th day of the month, right? And we just don't want to predict a value. You want to know the nature of this x3. You want to know what type of random variable is it, what is this mean, what is this variance, I want to know, right? So this is typically a machine learning setting. We give some training values x1, x2, and we want to predict for a new value x3. In other words, we are interested in this conditional. This is a prediction conditional. Prediction conditional. right? So that means we are trying to predict x3 from our so this is in machine learning terminology, this you can call as a test point, and this I can call as a training point. The advantage of this Gaussian process is that the conditional probability, that probability of a test point, given that, say this is the typical prediction scenario, you are given some values of the training points, you are given some past stock values, you want to predict a new stock value. Not only predict a single value, but predict this variation also. We predict this mean and sigma also. So it's a typical machine learning setting where x1, x2 are the training point, x3 is the test point. The advantage of this Gaussian process is that this conditional is a Gaussian with a known calculatable mu and sigma value, provided you know the distributions of x1, x2. This is a Gaussian. Okay, this is a Gaussian. And moment is a Gaussian, its mu and sigma will characterize the expected value and the variance and everything. We know a lot about x3 now. All you need to know, you know more actually than just a prediction. You know its uncertainty also. Okay, so that's why for calculating this conditional, Gaussian processes are very elegant and natural. They are just this. The moment you can make it to be a Gaussian with some known parameters, then things are very simple. Then we know a lot. It's a familiar domain. All right. So what I will do next is that so intuitively I have told you that this is a Gaussian. Of course, algebraic also you can derive from the properties. What we will do next is that we will okay, and this entire problem will solve as a GP regression problem. Let me write down the problem. Yeah, let me write down the problem. So you have a training set or a labeled training set. Which I called D as a collection x1, y1, x2, x is the input, y is the label. Okay, particularly I call x to be this vector and I call y, actually I could have called it as x and y, no sorry, well okay, capital Xn is something, this small xn is something else, y1, 2. Okay, this is my training set and I have a test set. Okay, let me call it. Note that what is the thing about the test set? Test set is that I know x, I don't know y. I have to predict y from x. So let me call it as xm, which is I want to predict for m number of tests. This I have to predict. This is unknown. This is unknown. I have to predict this. So actually, I am so in a special case, this test point can be, yeah. the special case, this test set can be a single point. Let me call it as X star. So this is a test point. This is a special case of a test set, only a single test point. And then I am interested in Y star. This is the test level, which I want to predict. So what is the regression problem? Regression problem. I am interested something called a predictive distribution, which is nothing but a conditional. What is the conditional? The conditional is I am interested in this random variable ym in general case and y star for a single point case. I am interested in the levels of the test given the input to the text points, which is because of course I need to know x for which I'll predict y, xn, the previous training points xn, and the previous levels again, basically d. Okay, so this conditional probability I would call as a predictive distribution. I'll call as a predictive distribution. So this probability will have a distribution. We'll see in the Gaussian process, this is a normal distribution with some mean and some variance. I'll estimate that. All right. So this is my so this is clear. This is my predict. In a special case, this will become for a single. If I want to predict, test set is only a single point. Test set is only a single point. I am interested in y star given x star in x value, because for a given x value I have to predict the y value. Y x is known, y is unknown. Given xn previous training points and yn previous levels. This probability I am interested. I'm interested in this random variable. I'm interested in the distribution of this random variable. I'll derive it as a normal and it will have a mean and a variation. The mean will give me the expected value of the level. I'm considering regression, so y is a continuous value. In classification, it will be integer. I am interested in the expected value of y star, and I am interested in the which is the mean of this normal distribution, and I am interested in the variance of this y star, which is the variance of this normal distribution. Okay, so let me take a quick break. I'll drink some water and come, and then we will do this derivation. Let me stop the recording. I'll come back in